the next type of actuators we're going to discuss are the piezoelectric actuators. So, piezoelectric actuators are based on piezoelectric materials. And what are those? Well, piezoelectric materials, or materials with piezoelectricity, have the ability, or they are ceramic crystal materials that have the ability to transform a strain into a voltage, or a voltage into a strain. So deforming the piezoelectric material will generate a voltage over it, and applying a voltage over the piezoelectric material will cause it to deform. Piezoelectric materials are actually used in our daily life a lot, actually, but we may not be aware of it. One example is a lighter, a simple lighter. Here you can see a little lighter where there's a gas canal here, and if you click here on the button, there will be a little flame coming, and you can use that, for example, to put on a candle. So how does this work? Well, if you're going to push here this button, what happens is that there's a gas stream coming out of here, and it comes here, out here. But at the same time, when you push, also what you do is you have to push rather hard. What you're doing is you're deforming a piezoelectric crystal at the top here. So by pressing this you generate a very high voltage over it, and this voltage is so high that you create an electrostatic discharge, an arc. So if you have a gas flow and this electrostatic discharge here, of course the gas will inflame at that moment, and you will get a burning that will start the burning of the gas. So piezoelectricity, where does it come from? As said, it is a property of certain crystals, not all crystals, only certain. And piezoelectric crystals typically have a crystal lattice that looks as follows. They consist typically of three different components. Component A, B, C, for example, that can be, in the most common material is called PZT, which means lead, zirconium, titanium. And then you see the atoms are, the lead and the zirconium and titanium atoms are in this configuration, and there is one small, the zirconium or the titanium is in a position that is not in the middle of the lattice but slightly off-centered. So it will be attracted to either this atom or to this atom. So you can see it has two different positions. And throughout my crystal lattice, these little black atoms here, they will be either in the top or in the bottom. So that will vary from crystal to crystal. And so what's going to happen is, if I'm going to compress this crystal like this, then I will deform the crystal and I will move this little black atom a little bit either to the middle or to the top. And so you get an electronic redistribution. There's an electronic, of course, the electrons between these atoms, there's a certain distribution function of those. And I will disturb that distribution. So the electrons in here, they are slightly redistributed. And that will cause that I create, over every small lattice part, I will create a certain net electrical field. So normally in a crystal material, the position of these zirconium or titanium little black atoms here is random. So when I compress my material, some are going to be pushed, for example, a little bit up, and some are going to be pushed a little bit down. So the net electric field of all this, the contribution of all this, billions of different crystal cells, will cancel out each other. However, if I pole my material, that means if I can get my material in a state where at all the crystal, or in most of the lattice, and most of the positions, for example, the atom is on the top side, if I can create that kind of state, then if I then compress my material, all these little electronic redistributions will add up to each other. So I'll actually gonna get a sum. So if I compress the material, I will get the net effect will be the sum of all these small contributions, and I'll get a real good output. So poling, how do I do that? Well, if I apply heat to this crystal, and I heat it up to above a temperature which is called the Curie temperature of the crystal. For P's delta T, this can be typically around 100-150 degrees Celsius. So above that temperature, this atom here has enough thermal energy to freely switch between this position and this position. Below the temperature, it will be typically frozen in one of the two positions. So what I do is, if I move it above the temperature, I get a random distribution very fast. But then if I put an electrostatic field, I can actually suck all these atoms to the upper position. So I pull them, so I put at high temperature and at a high electric field, all of the atoms will move to the preferred position. And then when I cool it down, keeping the electric field, they will be frozen all in this position, and I have pulled my material and it will work as a piezoelectric material. At the same time, I will have to see that during my operation, I will have a temperature limit, of course, because if I want to operate my piezoelectric material at a high temperature, for example, say above 150 degrees or above the Curie temperature, the material will lose its piezoelectric properties. How do you deal with piezoelectricity? There's something called the piezoelectric coefficient. A piezoelectric material is, of course, you can strain it in 3 different directions. No, you have different stress tensor. You can strain it in different ways, like horizontal, the vertical, and in the horizontal plane. And you can also shear it in 3 different directions. So you get 6 different stress terms. And then, of course, you also have an electric field or dielectric field in the 3 spatial dimensions. And so you can actually write this in a matrix form, like if you stress the material, so a certain stress of the material will be resolved by a certain strain and a certain change in E modulus. What is important to know is the magnitude order of piezoelectric force. So the strain is typically 1 millionth per volt. That means if I have, say, a 1 millimeter thick piezoelectric material and I put 1,000 volts over it, then it will strain typically 1 micrometer. So that's a very, very small effect. We're going to see in the next slide how we can use even this very small effect to get a good output. Another thing that is important to show here is that typically materials will be piezoelectric in the direct mode or in the shear mode. What that means is, in the direct mode, is that if I have a material and I put a field for example here in the vertical direction, then also it will contract or expand in the vertical direction depending on the direction of the field. So it will expand, for example, it will expand and become smaller, or contract and become thicker. In the shear mode, if I put these are different types of crystal, or they are differently poled. If I now put a electric field in the vertical direction, what's going to happen is that the material will shear. It will deform in the lateral direction. So putting a voltage will shear the material. Let's have a look at an example. Again, another example that we use in daily life. This little loudspeaker made of piezoelectric material. So what happens if I take a piezoelectric disc and I bind it to a diaphragm? It looks like a bimorph. Then if I then put a voltage over the disc here from the top to the bottom, what happens is that I can make the crystal, for example, contract in that direction, expand in that direction. And if I make it expand, what will happen is that it will force the entire structure to bend in this way. So here I have a diaphragm that will deform exactly in the exact same way as I put a voltage over it. So basically this is a loudspeaker. I can put a music signal here, and it will be converted in an electronic signal here will be converted into a sound signal here by the movement of the piezo diaphragm. And here you can see an example of such a loudspeaker. Having a picture of such a loudspeaker. You see close up here. This is actually an actual component. You can buy these in, for example, in Alpha. These components, they cost maybe £1 or something, or even less. If they're mass-produced, they cost really, really little. This is one you can see here, for example. This is the brass plate, and here what you see here, this ring here, that's the piezoelectric material. See, it's very thin. It's maybe 100 or 200 micron thick. And the white plate on top here is typically a platinum electrode. And then you solder to the platinum electrode. So this platinum electric field, you put an electric field to the platinum electrode and to the brass plate. And then the piezoelectric crystal is in between and will change its shape according to depending on the electric field. And here you see yet another component. Here it's another component fallen out. Here you can see the same thing, but in real. This kind of loudspeakers are used everywhere. Typically they're in your computer. When you start up a stationary computer, it often says boop. And so every motherboard of a computer has one of these loudspeakers on them typically. And they're not very high quality, but they're very cheap and very easy to build. For example, a singing Christmas card, they will typically contain a piezoelectric loudspeaker. So very cheap components. Here you see how you use a piezoelectric material make a bimorph between piezoelectric material and a brass plate. You can also do piezoelectric on piezoelectric, and then you can pull them either in the same direction or in the opposite direction, and then depending how you apply voltages or how you couple them, you can get either large displacement bimorphs or large force bimorphs. I'm not going to go in too much detail into this. However, I do think it's time for a little quiz. So we've been talking about piezoelectric materials, whereas before we've been talking about piezoresistive materials. These are different. So I want you to go back to your piezoresistive video, look at that and now your piezoelectric, and then give an answer to all the questions that are stating here. There's 6 statements, and you have to click, are they always, never, or sometimes true, or in this case, are they yes or no?